Hello my dear students and viewers. In this lecture, we are going to start a new unit of the course, that is theories for constraint optimization problems. We noticed that in the last few lectures, we were discussing about algorithms, methods for solving unconstrained optimization problems. Now we are on the aim of finding several methods to solve constraint optimization problems. Towards this, we need to talk a bit about theories or optimality conditions for constraint optimization problems. I guess we all have learned the Lagrange multiplier method to solve a constraint optimization problem subject to equality constraints. Now in this lecture, we are going to revisit this Lagrange multipliers rule to solve a constraint optimization problem. We will find that unless we are a bit mathematically careful while applying this Lagrange multipliers rule, then we may get a solution which might not be a solution of the constraint optimization problem. And after finishing a revisit on Lagrange multipliers method, we will get into learning several cones which will be useful to find optimality conditions for constraint optimization problems. In this class, our agenda are as follows. We will at first recall our knowledge about the Lagrange's multiplier rule for equality constraint problems that we have learned in our advanced calculus course, calculus for function of several variables. If we recall, in that course, mostly towards the end of that course, as an application of calculus for function of several variables, we have learned how to find a local minimum for a function of several variables subject to some equality constraints. There we have learned the Lagrange's multiplier rule. We will revisit that rule that we have learned. We shall see that the process that was discussed during the advanced calculus for identifying local minimum for a function of several variables subject to equality constraints, that was missing some mathematical points, and unless we are not careful about those mathematical points, then sometimes our conclusion out of the method that we have learned in our advanced calculus course, the Lagrange's method, that method might give us a misleading conclusion. We shall see what mathematics is said, and unless we are going to be careful about those points, then we may not be ending up with getting a local minimum by the Lagrange's multiplier rule. After revisiting the Lagrange's multiplier rule, we will try to find a few geometric optimality conditions from which we will find the most awaiting Karus-Kuntakar optimality condition for constraint optimization problem. Towards the development of the Karus-Kuntakar optimality condition, necessary and sufficient optimality condition for constraint optimization problems, we need to discuss a few particular types of cones. Those are related to the constraint as well as the objective function of a constraint optimization problem. There will be 5 specific types of cones. Those are dual cone, cone of feasible directions, linearizing cone, cone of descent directions, and tangent cone. In today's class, we will discuss out of these 5 cones, we will discuss 4 particular types of cones, and depending on these 4 particular types of cones, we will be trying to find a geometric optimality condition for a constraint optimization problem. And we will find that that particular geometric optimality condition, depending on these first four cones, that is little limited, and in order to enhance the limitation, in order to enhance the applicability of the geometric optimality condition, we will need a new type of cone that is called as the tangent cone. And with the help of the tangent cone, in the next class we will try to discuss geometric optimality condition. From there we will find the Karus-Kuntakar necessary optimality condition for a constraint optimization problem. So this class will be basically at first finding, or rather revisiting, the Lagrange's multiplier rule for equality constraints, and in the entire study on the constraint optimization problem, mostly we will find that the basic development is the Lagrange's multiplier rule, and keeping our attention around the Lagrange's multiplier rule, we will be able to identify optimality conditions for constraint optimization problems. Well, so let's start at first with just recalling the Lagrange's multiplier rule for equality constraint problems. What we have learned in our basic calculus course is the following, that if a problem of this type is given, that I have to find a local minimum of a function fx, say, subject to a few equality constraints subject to hjx is equal to 0. Let's suppose we have L many equalities, so the index j runs from 1 to till L, and here we assume that the variable x, that is general variable coming out from the n-dimensional Euclidean space. Fine, and we also assume here, unless otherwise stated, we assume that here the functions f and all ages for all j are continuously differentiable. We are under this assumption, and depending on this assumption, we have learned that the Lagrange's multiplier rule is applicable here, and the steps that we have followed in the Lagrange's multiplier rule are the following. Lagrange's multiplier rule. At first, what we have done in the first step, deliberately we construct the Lagrangian function that is given by Lx lambda, where lambda is a vector that consists of L many components, lambda 1, lambda 2, lambda L. Each of the component is corresponding to each of the constraint in the problem. So lambda 1 is associated to h1, lambda 2 is associated to h2, and lambda L is associated to hl. And we construct the Lagrangian function given by fx plus summation j is equal to 1 to L lambda j h jx. We deliberately construct this, and then what we do is, in the next step, is solve for a vector x lambda such that this x lambda satisfies del L del x is equal to 0, del L del lambda is equal to 0. By this del L del x, we mean it is the component of, here by del L del x, this sometimes also appropriately written as nebula with respect to x, L is equal to 0, and this del L del lambda, it is also sometimes appropriately written as nebula lambda L. These are notations, and this del L del lambda, by that we mean we have here these components, del L del lambda 1 first component, lambda has L many components, and therefore you have the second component as del L del lambda 2, and the Lth component is your del L del lambda L. Fine, this is equal to 0. And similarly, del L del x, here you will have n many components. First component will be partial derivative of L with respect to x, second component partial derivative with respect to x2, and the last component is the partial derivative of capital L
the Lagrangian function with respect to the nth variable xn. Fine. Solve this system of equations, and here obviously this is nothing but del L del lambda 1 is nothing but h1, and the last component is hl is equal to 0. So these things all of you are aware with. And in the next step, last step, what you do is the following. In the last step, the step 3 in the Lagrange's multiplier rule, you do the following, that find the set S consisting of those x's for which associated to x you have a lambda that solves the system. Let's suppose this system, let me call it as stationarity system, solves is t. Fine. So in the step 2 you have identified a set of possible x associated to x, you have a lambda. So set of possible x lambda vectors which are satisfying this stationarity system del L del x is equal to 0 and del L del lambda is equal to 0. Now here, out of those x lambdas, those are satisfying the stationarity condition, you find the vectors x's, and those collection of x's is constituting the set capital S. Now in this set, in the set capital S, you have collection of x's for which associated to each x you have a lambda such that x lambda solves st. Now here, out of the points x's, those are in capital S, you find the minimum most value, of the function fx where x is lying in capital S. Let me denote here with x dash so that we are not going to be confused with that this x is a general variable. This x is not a general variable. These x's are particular values of x's. Let me denote it by x bar. Associated to x bar you have a lambda bar such that x bar lambda bar solves st. Then you find the minimum most value of the function f only on the set S. That means you find those points, those x bars in S which gives minimum value of f. Let's suppose in S you have a few points. Let's suppose x1, x2. Let's suppose you have xk. Maybe this set may consist infinitely many elements, but let me suppose that it has these many elements. So out of this x1, x2, xk's, you find, obviously let me consider here x1 bar, x2 bar, xk bar. These are not components. These x1, x2, xk's are not component of x bar. Here these are k many x bars. So out of these k many x bars, you find the minimum most value of the function f. Let's suppose xp is giving minimum most value of the function f on the set S. Then you declare this xp bar as the local minimum of the function f subject to the constraints that this problem, subject to the constraint that ajx is equal to 0. Now here let me put a question. Does this method really give a local minimum for the function f subject to a set of equalities in general setting? That means I consider a general problem where I have f and all aj's are continuously differentiable and I follow all these three steps. My question is it really the case? Is it really true that for every problem you are going to get a local minimum value for the function f subject to the given constraints? The answer is no. And we remark here that we need to be mathematically careful when adopting the above three steps to solve the optimization problem fx. subject to the constraints hjx is equal to 0. So here we need to be careful for the following 2 points. Where is the loophole going to get? Where we are going to get loopholes in this method? Why the answer is no, that this method, if we deliberately apply for a constraint optimization problem with equality constraints, this method might be giving a point that is not really local minimum for the function fx. The first point is the following, that in a step 2, what we are assuming that the possible candidates, possible x's for which you have an associated lambda, such that this x lambda satisfies this del L del x equals to 0 and del L del lambda equals to 0. In this step, here the point is this system of stationarity might be inconsistent at a local minimum. Once it is inconsistent, then in that case you have no x lambda which is solving this system, stationarity system, and accordingly you will not have the step 3, and obviously you are not going to get a solution by this method. This is the first point. So we need to be careful. The first careful point, let me just write here, careful one, is that we are deliberately thinking that in step 2 we are going to get a solution, at least a solution x for which you have a lambda such that x lambda is solving the stationarity system. That is not always true, and rather that a local minimum point might not be a solution of this stationarity system if the problem is not satisfying a regularity assumption. If the problem, in addition to just f and h, j's are continuously differentiable, in addition to this condition, we need something extra condition to be imposed in the problem such that a local minimum will be a solution for the stationarity system. So here the first point, let me write out, without a regularity condition, a local minimum may not satisfy the stationarity system. And by regularity condition we mean some condition on the function f and h such that the local minimum must be a solution for the stationarity system, and those are broadly in optimization theory, those are called as constraint qualification. We'll have a separate rigorous discussion about this regularity condition or constraint qualification. Here I mention here regularity condition and also constraint qualification. By constraint qualification I am not meaning I do not mean that by this constraint term I do not mean the constraint of the objective function. By this terminology constraint we mean the constraint which is stopping us to declare that a local minimum is a solution for the stationarity system, and that's why it is nomenclatured as constraint qualification. However, more good term will be regularity condition. Anyway, so without a regularity condition, therefore the stationarity system may be inconsistent at a local minimum of the given problem. So this we have to be careful. Second point is in the step 3. Here you note that in the step 3 you are collecting those x bars which are satisfying the stationarity system, but deliberately you are declaring that x bar is a local minimum without an extra check that a point is that gives a minimum most value must satisfy that the Hessian matrix is positive definite or so, like the second order sufficient condition that we have checked for unconstrained optimization problem. In the unconstrained optimization problem we know that the stationarity condition grad f is equal to 0, a solution for grad f equals to 0 may not be a local minimum. So in the step 3, what you are doing, you are just declaring that a solution of the stationarity system is a local minimum. This is not, obviously not fair, and therefore in the step 3 your conclusion may be misleading without an extra check. Extra check will be in our course a second order optimality condition that has to be checked, second order sufficient condition. Obviously that second order sufficient condition will be depending on the Hessian of the Lagrangian function, and if that Hessian of the Lagrangian function is positive definite in some particular cone of directions, then we can declare, that will suffice to say that, well, your x bar point is really a local minimum of the given problem. Fine. So without an extra check, step 3 might be misleading. Fine. Careful 2. In careful 2 we have the following, that extra check obviously depending on, maybe depending the Hessian matrix of the function L. For these 2 points, careful 1 and careful 2, let me consider 2 particular problem, and let me show you really that we need to be careful about the first and the second point, and if you are not careful, your answer might be wrong. For the first point, let me consider the following example. Example 1. Here you consider the following problem. Consider the problem that is asking us to find a minimum value of the function x1 plus x2 subject to x1 minus 1 square of it plus x2 square less than equals to 1, x1 minus 2 square plus x2 square less than equals to 4. Well, I'm mentioning here this Lagrange's multiplier for equality constraints, and by a quick graphs of these constraint functions h1 and h2, you can find what is a solution for this problem. Obviously the solution of the problem is the origin, because origin is the only feasible point here. Because if I just quickly draw the graphs for the first and the second constraints, then you will find the following graph. Okay, this is my x1 axis, this is my x2 axis, and first constraint is the circle of radius 1 centering at 1 0, and the second circle is circle of radius 2 having center at 2 0. Fine. And both are equal to 1, that means both are equality constraints, and therefore you have only feasible point, the origin, right? Origin is the only feasible point here, and obviously this point origin is indeed the local minimum or indeed the global minimum for this problem, right? And here what to note is the following, that what are the gradients at the origin. The gradients at the origin are the following. For the first constraint, for this smaller circle at origin, you have the gradient is obviously outwards direction. This is your gradient, right? Similarly, for the bigger circle also, the same type of direction you have, same direction, and this is your gradient direction, right? And therefore what we have, then gradient for the function h1 at the point 0 0, and here let me mention what are your h1s and h2. h1 x1 x2 is equal to the function x1 minus 1 square plus x2 square minus 1, right? Then only h1 x1 x2 is equal to 0 will give the first constraint. Similarly, h2 x1 x2 is the function x1 minus 2 square plus x2 square minus 4. Fine. And here also the objective function is if x1 x2 is equal to x1 plus x2, right? Now let me quickly calculate the gradients, because gradients will be needed in the gradient of the Lagrangian function. In that we will need all these gradients. For the objective function, what is the gradient? Obviously the gradient is the vector 1 1, right? And for h1, in general point, it will be first component will be 2 times x1 minus 1. So at 0 0 you will have here minus 2, and second component you check, second component will be 0. Similarly for h2 you will have the vector minus 4 0. Now deliberately apply the Lagrangian method, that in the step 1 you construct the Lagrangian function L, x1, x2. You have two variables and you have two constraints, and therefore you will consider two lambdas, lambda 1, lambda 2, and this will be given by f x1 x2 plus lambda 1 h1 x1 x2 plus lambda 2 h2 x1 x2, right? And after the Lagrangian, then in the second step, in the step 2, what you do? In the step 2 we consider del L, del X and del L, del lambda, both are equal to 0, or this vector is nothing but precisely we can just think this is gradient of L. And here gradient of L, obviously you have for many components. In del L del X you have two components with respect to x1 and with respect to x2. Similarly in del L del lambda you have two components with respect to lambda 1 and with respect to lambda 2, right? Here you have nebula L, the gradient of L, x1 x2 lambda 1 lambda 2. This will give us the four components as well. So in the second step, we are now in the second step. In the second step, it is asking that you find a solution X together with a lambda that satisfies this stationarity system, right? And let us now consider the first component of this stationarity system. This is equivalent to at 0 0. At 0 0, this stationarity system is the following, that grad f 0 0 plus lambda 1 grad h1 0 0 plus lambda 2 grad h2 0 0 is equal to 0, and you have obviously the second components, those are 0 and h2 0 0 equal to 0. Obviously these two conditions are satisfied. However, for the first one, do we have really lambda 1 lambda 2 for which the first condition is satisfied? Obviously no. This is due to the following fact. The first equation gives. Now, do we have any lambda 1 lambda 2 such that both the sides are equal? No, really, because here you note that from these two vectors the second component is 0, right? And here so 1 plus 0, so this will give us on the left hand side whatever be the component in the first, but in the second component you have 1 and on the right side you have 0 0, right? And this cannot be possible. 1 is equal to 0, and therefore you don't have any lambda 1 lambda 2 associated to the point 0 0, which is really local minimum for the point, but you don't have associated lambda 1 lambda 2 such that the point 0 0 together with those lambda 1 lambda 2 will satisfy the stationarity system. and therefore a local minimum, here you note that a local minimum evidently is not a solution of the system that we have constructed in the step 2. So in this step 2 we have constructed this system and we deliberately feel that at a local minimum x bar there must exist one lambda bar such that x bar lambda bar is the solution, because if we are not thinking that there might not exist one lambda, then obviously that particular x will not come into the set S, and therefore your local minimum is missed out, right? And not only local minimum, obviously your global minimum also can be missed out, and that is what happening in this example. In the example 1 we know that you deliberately apply the Lagrange's multiplier rule, and ultimately what you are going to get is that the step 2 does not have a solution, or the step 2 is not satisfied by the global minimum for this problem. We need to be careful at the first point that without a regularity condition, a local minimum may not satisfy the stationarity condition. Fine. Now here repeatedly I am saying stationarity condition. Some of you might be confused with. By stationarity condition, what do we mean? By stationarity condition, we mean this word stationarity is coming from the stationary point. Now for a stationary point, what do we know? For a point is a stationary point. Let's suppose I have a point, let's suppose y, and that point y is called a stationary point of a function, let's suppose theta, if gradient of theta of y is equal to 0. Fine. And this system grad y is equal to 0 is called stationarity system. Fine. And that's why this system that I encircled here is indeed the stationarity system for the Lagrangian function L. That's why I'm many times referring it as a stationarity system. Well, so this example goes with the careful one, that you need to be careful really, that without a regularity condition, without an extra condition satisfied by the objective and the constant function, a local minimum may not be a solution of the stationarity system, or a local minimum might not be a stationary point for the Lagrangian function. And for the careful 2, let me consider the following example. Example for careful 2. Now here you consider the problem try to solve this problem with the help of the Lagrange's multiplier rule. If we deliberately apply the Lagrange's multiplier rule, what we shall do is, at first we will construct Lagrange's function L x lambda. X has two components, x1 x2, and that is given by the objective function plus lambda times x1 plus x2 minus 4, right? This is your Lagrangian function. Then the stationarity system for this problem is, at first with respect to x, if I take partial derivatives, then you will have del L del lambda will give us, and from here you try to solve for x and lambda, and you can quickly find from the first equation that this is going to give x1 is equal to x2 is equal to minus lambda, and from the second equation x1 plus x2 is equal to 4, you are going to get the value is equal to 2. And therefore what is the set? S, capital S, the collection of those x's such that associated to the x's you have lambda such that x lambda is satisfying this stationarity system, and therefore S consists only the point 2 2, right? Because corresponding to this point 2 2 you have a lambda given by minus 2 such that this x bar together with this lambda bar, x bar lambda bar, is a solution of this stationarity system. And once you have a single point in the set S, obviously by the Lagrange's multiplier rule declares that the point 2 2 is a local minimum. By the Lagrange's method, you are going to get this is the conclusion, right? That 2 2 is a local minimum of the function x1 x2. Now, is it true really? If you just geometrically try to see what is your constraint set and what is your objective function, then you will find the following: that x1 plus x2 is equal to 4. That is this line, say this line. And what are the contours for this objective function x1 x2? The contours of the objective function, if I start with some positive values, let's suppose 8 at first. x1 x2 is equal to 8. That gives this rectangular hyperbola, as well as on a third quadrant you will have a counterpart. Similarly, this is, let's suppose this is for f is equal to 8. Similarly, f is equal to let's suppose 6 will be this hyperbola, f is equals to 6. Similarly, f is equal to 4 will be this one. Fine. And here is your the location 2 2, and you may feel 2 2 is a local minimum point, but obviously not, because this function f is equal to x1 into x2. This function decreases indefinitely in the line x1 x2, because obviously we know that if I consider this particular point, which is some, let's suppose, let me give a particular value. Let's suppose I have here -1 and I have here y value is equal to, let's suppose, 5. Then x1 is equals to -5, and you have the contour passing through this point is this contour, right? And similarly, here is a -5. You could go further and you will have much more negative value, right? And therefore we note that in x1 plus x2 equals to 4, in this line the objective function reduces indefinitely. In fact, this objective function is unbounded below in the constraint set x1 plus x2 is equal to 4, and therefore this problem does not have any solution. But the Lagrange's multiplier rule is saying that it has a solution, and the point 2 2 is a local minimum point. Fine. Here let me repeat once again the Lagrange's multiplier rule. Several times I am referring the Lagrange's multiplier rule, rather I should refer Lagrange's multiplier rule that we have learned in our advanced calculus course, calculus for function of several variables. Typically in IIT BHU we have learned at the first year mathematics 1 course, we have learned this Lagrange's multiplier rule. And as we did not have much chances to discuss rigorously the Lagrange's multiplier rule, what is hidden in the method, we have just mentioned during the course due to time crunch and everything. We have just mentioned this is your method and let you apply and find a solution. So let you learn the tool in mathematics 1 and learn the method in the mathematics 1, at least the taste of the method. Then later on the nitty-gritty of the methods will be learned in the higher level course. This optimization course, which is assumed to be higher level because this is floated open elective, and here we are now observing that the Lagrange's multiplier rule or the method of Lagrange's multiplier that we have learned in mathematics 1 obviously need to be, in order to apply that method we need to be careful about 2 points, careful 1 and careful 2. And now next, then, what are the particular regularity condition that we need to impose on the objective and constant function? And similarly, in step 3, what should be an extra check such that a point in the set capital S must be a local minimum point? So our next few lectures will be endeavoring on identifying a few regularity conditions or constant qualifications, as well as the second order sufficient optimality condition, so that on capital S you consider a point that gives minimum most value, and then that particular point x bar, for that point x bar which you are tempting to conclude that that point x bar is a local minimum, but unless you check the positive definiteness of the Lagrangian function, Hessian of the Lagrangian function, then it might be misleading. And that gives you the one example here. For careful to, in this example here, we note that we did not check any Hessian of the Lagrangian function. Without checking, we have just declared that this point 2 is a local minimum. Fine. Now, in order to be ready with identifying the regularity conditions, a few regularity conditions, I must at first discuss a few geometrical notions on the constraint sets as well as for the objective function. Those are dual cones, and next we will try to discuss about the cone of feasible directions, linearizing cone, and the cone of descent directions. And later on we will consider to discuss about the tangent cone on the constraint set. Fine, so let me start then discussing the idea of dual cone. Dual cone for a given subset of the n-dimensional Euclidean space. So we let C be a non-empty subset of the n-dimensional Euclidean space. Then the set we shall denote it by C star, defined by set of all those vectors in Rn such that the inner product of y and x is greater than or equals to 0 for all x belonging to C. This inner product idea we have learnt in linear algebra, and unless otherwise specified, this inner product of a pair of vectors in the n-dimensional Euclidean space is nothing but the matrix product that y transpose x. Fine. So what does this star geometrically saying? It says the following, that you collect those points, those vectors, rather those directions in Rn such that y transpose x is greater than or equals to 0 for all x belonging to C. By that we mean, let's suppose this is my set of points C including boundary here, and in the dual cone C star, those vectors are to be included. Let's suppose this is my origin in the R2 plane and C is the set. What does it say? That you include those vectors in the cone, those vectors, not necessarily in C. You note that y can be any vector out of C as well. For instance, let me consider this direction, and it says that this direction y can be a possible candidate, can be inside the set C star, provided that y transpose x is greater than or equal to 0 for all x belonging to C. By that we mean, what is the geometry for this? Y transpose x is equal to greater than or equals to 0. Y transpose x equals to 0 is what? Y transpose x is equal to 0 is the hyperplane for which the perpendicular is the vector y, and therefore for this y we note that y transpose x is this line that is perpendicular to y and passing through origin, right? So this is your y transpose x is equal to 0, and this y can be inside the set C star provided y transpose x is greater than 0 for every x in C. That means in one side, that means the entire set C is in one side of the hyperplane, right? In one side of this hyperplane y transpose is equals to 0. Not only it is one side, but also it says the following, that this y can be a candidate of C star provided not only in one side of the hyperplane the set C lies, but also that any vector you consider in the set C, that vector must make an angle lesser than or equal to 90 degree with y, right? Because here the inner product is greater than equal to 0. By that obviously the angle between x and y can be in between 0 and the 90 degree, right? And therefore obviously here in the figure this y that I drew obviously is a possible candidate, because the set of all directions in C are this extreme. This is your bottom extreme, and the up extreme direction on C is this direction, right? And this y that I have drawn, obviously that makes an angle, maximum angle is this much, right? Maximum angle is this much with this vector, with this particular vector in C, and obviously that makes, obviously y makes an acute angle with all directions in the vector C, right? And therefore now let us geometrically identify what is the set C star for the set C that I have drawn in this figure. And you note that obviously the set C star will be those collections of y vectors that are making angle not more than 90 degree. And therefore here in the bottom you have this much is the bottom direction, and you take perpendicular to it, maximum possible spread will be this much in C star, and for the off direction, this direction, you take the perpendicular to it. The perpendicular to it is here, this angle is perpendicular, this angle is 90 degree. Similarly, this angle is 90 degree, right? And therefore the set C star is set of all these red points in between the two red lines, red directions that I have drawn. Because here you note that any direction in between these two red directions, let me pick up a direction arbitrarily, let me choose this direction. Here you note that this direction obviously makes an angle not more than 90 degree with all the vectors in C. Maximum angle is this much, and obviously that is lesser than 90 degree. And if I consider a direction of this, then obviously the angle, the maximum angle is this much, and this maximum angle is obviously more than 90 degree, and therefore this direction is not there in C star. Fine. And therefore now we declare that for the figure that I have drawn, the set C star is this red dotted region. Fine. This is your C star, and geometrically in R2 plane we have identified what is your C star. And now next let me consider a few examples, and we find the dual cone. Why this dual cone is important is the following. We note that the dual cone, the definition itself says that the maximum angle with the dual cone, with the vectors in the dual cone with the set C, obviously not more than 90 degree, and this condition is somehow there in the notion of the descent direction. You note that a direction D is descent for a given function f at the point x bar if gradient fx bar d is less than 0, right? And therefore we note that obviously if grad f x bar is inside the set C, the element, the set of all directions, those are descent, must not be belonging to the set C star. It's not that. So somehow the notion of descency, the direction at which you may be tempting to move ahead to reduce your function, obviously is not in the dual cone of the set C, which includes the vector grad f x bar. Right? and that's why this dual cone is needed. And we'll obviously, with the help of the dual cone, we'll have several geometric optimality condition, from where we will have algebraic optimality condition. Let me now consider a few examples where the dual cones are to be identified. The first example, example 1. Now find the dual cone for the set C that is given by those points x1, x2 which are lying in the periphery of the unit circle. X1 square plus x2 square is equal to 1. Fine. What are the possible directions in the dual cone for the set C? And here we note that the points on the set C are the points on the periphery of this unit circle, right? Periphery of this unit circle. Now can you attempt on your own to find what are the possible directions in the dual cone for this set C? And it will be very interesting to find what are the dual cone for this set. You note that any direction you consider, whatever direction you take up, let's suppose I take a direction D, and non-null direction I am taking, let's suppose my direction is non-zero or non-null direction, and I take the components as D1, D2. Now with this D1, D2, we note that for any D, for any non-null D, you construct a vector x, rather let me denote it by xd, given by minus d by norm d. Obviously this is inside the set C. Fine. And hence, and note that this, and you have xd transpose the direction d is equal to minus 1, right? Minus, so not exactly minus 1, let me divide then by norm d square. Then you will have x transpose d is equal to d transpose d, and that is your norm d square divided by norm d square minus 1, and that is less than 0. And what does this inequality says? This inequality says that the direction d obviously is not in sister, because you have at least one direction x, at least one element xd in the set C, such that the angle between xd and d is more than 90 degree, and therefore d is not belonging to C star. So any non-null direction is not in C star. And what about the null direction? Obviously by the definition itself, we know that by the definition itself, and that of C star, the definition of C star itself says that 0, the null vector, the origin, must be belonging to C star. It's not that, because here you note that if I take y equal to null, then the null vector times any vector you take x, that will be equal to 0, and obviously satisfying greater than equals to 0. And therefore the null vector must always be inside the dual cone, and therefore, and hence, the set C star is consisting of only the null vector, the origin of the R2 plane.
Oh, I am sorry here. This xd that I have written here, minus d divided by norm d square, it is not in capital C. Sorry, because norm of xd square is not equal to 1. To make xd inside C, we need to take minus d divided by norm d, and that will make xd transpose d is equal to minus norm d, and that is still again negative. So analysis will persist, the same analysis will go, but we need a modification. Let you please make a modification. For a given non-null vector d, you please go for constructing xd, which is equal to minus d divided by norm d, and that will be belonging to capital C,
and accordingly you will find that the dual cone for the set capital C is consisting only the null vector, the origin of R2 plane. Okay, now let me consider the example 2 where I include the points as follows. X1 x2 in R2 is the set of all points on the periphery of the circle having center 1 1 and having radius is equal to 1. Fine, this is my set C. Now can you be able to identify what is the dual cone for this set C? Let me quickly graph out the elements in C. Here you note that the elements in C are, here is my circle, center of the circle point, and then I have, fine, and now from the graph itself it is very easy to identify what are the elements in the dual cone system. What are the elements? Here you note that the elements in C, they give the directions as follows. This is one direction that is inside C. This is one direction that is inside C. This is one direction that is inside C. This is one direction that is inside C, and so on, right? And therefore, what are the extreme directions of the set C? The extreme directions are the positive x1 axis and positive x2 axis. Those are the extreme directions, right? The extreme directions for this set C are these directions. This is your positive x1 axis, this is direction, and this is your the extreme direction, right? And now by the dual cone, in the from the figure of the dual cone, how did we find the dual cone? And note that this extreme red direction is nothing but perpendicular to the extreme direction, this direction, and another extreme direction is this one, and for this extreme direction you find the perpendicular to it, and set of all points in between these perpendicular directions to the extreme directions in C, they will constitute the dual cone. And therefore here you note that the extreme directions are itself perpendicular to each other, and therefore C star will include set of all points, set of all directions D, D1, D2, such that is D1, D2 are D1 is greater than equals to 0 and D2 greater than equals to 5. And these usually we denote by the positive quadrant, that we denote by is R2 plus. Fine. Now let me consider another example. Example 2. Example 3. Now let me consider C is equal to set of all those points x1, x2 in R2 such that x1 minus 1 square plus x2 minus 1 square less than equals to 1 by 5. This circle let me consider, and let me find what is the dual cone system. Here you note that in the set C you could also consider, instead of equality, if I take less than equal to 1 for the set C with less than equal to 1 also, the same set C star is the dual cone for the set C with less than equal to 1. Now here set C has the following graph, that it is a circle centering at 1 1 and having radius 1 by under root 5, right? This is my circle, and here the extreme directions are obviously this tangent to the circle, and another extreme direction is this tangent to the circle, right? And accordingly the dual cone will be, evidently you draw perpendicular to this line, this red line, and therefore set of all points in this red dotted region is the dual cone. Now this is sufficient hint how to find the dual cone. Now can you be able to identify, can you express it mathematically, what is C star? I am giving you the answer and let you check the correctness of this answer. Well, so with this I end up the class here, and on the next day we will start our discussion in the topic of four other cones. The cones, those are left over today. Those are cone of descent directions, cone of feasible directions, then tangent cone, and also the linearizing cone. And then next, with the help of them, we'll slowly move towards the KKT necessary optimality condition for constraint optimization problem. Fine. On the next day, our endeavor will be a rigorous discussion about these four cones and identification of two geometrical necessary optimality condition depending on these four cone together with the dual cone that I have discussed today. Well, let me stop here. Thank you.